Hello students, welcome to the lecture number 1 on course Mechanical System Design. Myself Professor D.V. Kushare. In this first lecture we'll see prerequisites for this course objectives, contents, module number 1 design of cylinders and pressure vessels, cylindrical vessel, types of cylindrical vessel, stresses in thin cylinder. Next, course Mechanical System Design. Prerequisites for this course: the knowledge of the following subjects are required: engineering mechanics, manufacturing process, strength of materials, machine design, engineering mathematics, theory of machines, dynamics of machinery, and IC engines. Course objectives: to develop competency for system visualization and design, to enable students to design cylinders and pressure vessels and to use IS code, to enable students select materials and to design IC engine components, to introduce students to optimum design and use optimization methods to design mechanical components, to enable students to design machine tool gearbox, to enable students to design material handling systems, and ability to apply the statistical consideration in design and analyze the effects and failure mode in component. Module number 1 design of cylinders and pressure vessels. Now we'll see the contents of this module number 1. Design of cylinders, thin and thick cylinders, Lamè's equation, Clavarino's equation, and Bernoulli's equation. Design of hydraulic and pneumatic cylinders, autofrettage and compound cylinders, gasketed joints in cylindrical vessels. Design of pressure vessel, modes of failure in pressure vessels, unfired pressure vessels, classification of pressure vessels as per IS code 2825, categories and type of welded joints, welded joint efficiency. Stresses induced in pressure vessels, materials for pressure vessel, thickness of cylindrical cells, and design of enclosures as per IS code. Nozzles and openings in pressure vessels, reinforcement of openings in shell and enclosures, area compensation method, types of vessel supports. Next, design of cylinders and pressure vessels. Now what is cylinder? Cylinder is a mechanical device used for storing, receiving, processing, or carrying fluid. Example: pressure vessel, storage vessel, hydraulic devices, engine cylinder, pipe, etc. Now cylindrical pressure vessels are divided into two groups: thin and thick cylinder. Now what is thin cylinder? When D by T ratio it is greater than 20, that cylinder it is called as thin cylinder. Now Di, that is the inside diameter of the cylinder, and T, that is the cylinder wall thickness. When this ratio it is greater than 20, that is called as thin cylinder. Now next, thick cylinder. When ratio D by T it is less than or equal to 20, that cylinder is called as thick cylinder. Now next, pressure vessel. Now see, this is a typical diagram of the pressure vessel. It consists of this cylindrical shell, then this called as a enclosures, and this support. Next, stresses in thin cylinders. There are two principal stresses in thin cylinder, the circumferential or tangential stress sigma T and longitudinal stress sigma L. It is assumed that the stresses are uniformly distributed over the wall thickness. The stresses in thin cylinder. Now see the diagram A. It consists of the half portion of the cylinder, the Pi, that is the inside pressure, Di, inside diameter of the cylinder, sigma T, that is the circumferential or tangential stress, T, that is the cylinder wall thickness. So diagram B, it consists of this Pi, that is the inside pressure, then Di, diameter of the cylinder, and sigma L, that is called as a longitudinal stress. So it is acting along the axis of the cylinder, and T, that is a wall thickness. Now next, the circumferential stress. Now consider the equilibrium of the vertical forces which are acting on the half portion of the cylinder. Circumferential stress sigma T, it is given by Pi into Di into L, that is equal to sigma T 2T into L. Now this Pi, that is acting on this area Di into L. So at the equilibrium of the forces, this force, that is equal to this induced force, that is sigma T 2T L. So sigma T, it is equal to Pi Di upon 2T. Longitudinal stress sigma L. So it is given by Pi into bracket pi by 4 into Di square, that is equal to sigma L pi Di into T. So sigma L, that is equal to Pi Di upon 4T. It is seen that the circumferential stress sigma T is twice the longitudinal stress sigma L. In case of thin cylinders subjected to internal pressure, the circumferential stress should be the criteria for determining the cylinder wall thickness. Therefore, the design of thin cylinder is based on the circumferential stress. Next, stresses in thin cylinders. The equation of circumferential stress is rewritten as T, it is equal to Pi into Di upon 2 sigma all, where sigma all, that is equal to allowable tensile stress for cylindrical material. Now see, in the above equation, the efficiency of the welded joint, that is not considered. So considering the efficiency of the longitudinal joint, the above equation become T, it is equal to Pi into Di upon 2 sigma all into eta L, where eta L, that is equal to efficiency of longitudinal joint. Now next we'll see thin spherical vessels. Now we see this is a diagram of the thin spherical vessel. Pi, that is a inside pressure, Di, that is the inside diameter of the spherical vessel, sigma T, that is a circumferential stress. Now at the equilibrium of these forces, we get the relation Pi into bracket pi by 4 Di square, that is equal to sigma T into pi into Di into T. So sigma T, it is equal to Pi into Di upon 4T. So thickness of this spherical vessel, it is given by T, it is equal to Pi into Di upon 4 sigma allowable. The volume V of the cell is given by the relation V, it is equal to in bracket pi by 6 into Di cube, and the diameter of this spherical vessel, that is given by the relation Di, it is equal to in bracket 6V upon pi bracket raised to 1 by